Hey everyone, here's Hyperbola Day 1 notes. You can use the worksheet that you got in class unless you are in my earlier classes where I did not get the notes to you because I didn't have them yet. But you can print those out or you can wait to get this copy whenever I see you in class tomorrow. But make sure you at least copy down the examples you'll see towards the end of this video. Okay, so the set definition is a hyperbola is a set of all points x, y in a plane such that the difference of the distances between x, y, and two fixed points, the foci, is a constant. So it's almost the same thing as an ellipse, except now we have the difference instead of this sum. So we'll have a constant difference instead of a constant sum. Then for the conic definition, a hyperbola is an open curve formed by the intersection of a double-napped cone and a plane that is perpendicular to the base of the cone or parallel to the axis of the cone. So remember that whenever we had, I'm by no means an artist here, but we had a double napped cone. This would be if we had a plane that cut it vertically like that. And so then if you looked at that plane, that would make a hyperbola. Okay, and a hyperbola always has two branches. So here we have two pictures of a hyperbola. On the left, we've got the horizontal hyperbola, and then on the right we've got the vertical. So this one opens left and right, so it's horizontal. This one opens up and down, so it's vertical. Good thing about this is that it's going to be a lot like the ellipses, and so the A, B, and the C and everything like that will still be the same. So here we'll have from the center to a, let's just label the things we've known before. From the center to a vertex, remember that was the distance A. From the center to a co-vertex, that was the distance B. And then from the center to either of the foci, that was the distance C. So notice for a hyperbola, C is on the outside of A instead of inside. So C will always be longer than A for these hyperbolas. Now we also have two axes. Instead of the major axis and the minor axis of an ellipse, we'll have the transverse axis and the conjugate axis. To remember these, the transverse axis will connect between, will go through the vertices, so see the word VER, or the letters VER, and then for the co-vertices connecting between those, we have the conjugate, so you have the CO and the CO. So conjugate axis is between co-vertices, transverse is between the vertices. You'll also notice we have these dashed lines. Those are not axes, but these are the asymptotes of our graph, and we'll have two. So what we're going to end up having is a rectangle and then connecting the corners with the asymptotes. And then you can see the same thing, except this is a vertical hyperbola, but everything is labeled in the same way. From the center to a vertex is A, from the center to a co-vertex is B, and from the center to either of the foci is C. Okay, so let's look at the equations of these. Okay, so for a horizontal hyperbola, the branches open to the left and the right. So if you're looking at this formula right here, it looks a whole lot like the ellipses, but we have a minus sign because remember we have the constant difference here. But we have the x minus h squared, we got the y minus k squared, and over a squared and b squared. So this looks just like the ellipse except for being horizontal, except there's a minus sign. But on ellipses, to figure out if it's horizontal or vertical, we switch the a and the b. But for hyperbolas, we switch the numerators, the x and the y. So a and b, the a squared and b squared, are always in the same place with a minus sign in between, always equal to 1. But it's horizontal if you have your x minus h on the left, and it's vertical if you have your x minus h on the right. The center, however, is still the same. So in these parentheses, the x came first, so this first value, that would be the x value for the vertex. This would be the y value. Opposite sign because see it's set up as a minus. So that would be our x and our y for the vertex, center. But then for the center on this one, because the x was second, just be careful when that happens. This is still going to be the x, and this will be in the y. It's just going to be in the opposite order. So the center would still be at xy or hk here, opposite sign. When we have a squared and b squared, We have a little note right here we'll check out. A squared is always the denominator of the first term, the positive term, in a hyperbola. And there are three possibilities in a hyperbola. So A can be bigger than A, it can be A can be bigger than B, it can be less than B, or it can be equal to B. Unlike an ellipse where A was always bigger than B. So let's go ahead and jump into a couple of examples. On your notes page there are a bunch of other words down there, and I would love for you to read those, but we're going to go ahead and start using these examples in this next section. And real quick, just before we start graphing these, let's look at these three things. We have the central rectangle of the hyperbola, which I noted in that picture. And so a rectangle formed by the endpoints of transverse and conjugate axes whose sides A and B units away from the center. These are used to sketch the asymptotes. So once you know where the axes are, it makes it really easy to find the asymptotes. And the asymptotes are lines which a branch of the hyperbola approach but never intersect. The asymptotes are the lines that contain the diagonals of the central rectangle. So we'll take the central rectangle and connect the corners to get the asymptotes. And they intersect at the center of the hyperbola. And then finally, the eccentricity of a hyperbola. Same formula as for an ellipse, E equals C over A. But since C is always greater than A in a hyperbola, the eccentricity of a hyperbola is always going to be bigger than 1. The greater the eccentricity, the wider the hyperbola. Okay, now let's work a couple of examples. Okay, so for this example on the left, we have x minus 1 squared over 16 minus y plus 3 squared over 9 equals 1. So for the center, we look at the x, the y, opposite signs. We'll have a center at 1, negative 3. Remember, for the hyperbola, the a squared is always first and b squared is always second. So a squared is 16, so a is 4. B squared is 9, so b is 3. And for an ellipse, we use the formula c squared equals a squared minus b squared. But for a hyperbola, because the c is on the outside of the a, we're going to actually use the Pythagorean theorem. C squared equals a squared plus b squared. So we have c squared equals 16 plus 9. So c squared is 25. Therefore c, the square root of 25, we get 5. So let's plot what we have so far. We know the center is at 1, negative 3. And a is going to be the distance from the center to a vertex. But to figure out which way we're going to be going, since the x was first, that's what told us that this is going to be horizontal. So, because it's horizontal, the a from the center to the vertex will be going horizontally as well. So we're going to go to the left and the right 4. C always goes in the same direction as A. We'll get back to that in just a second. But B will go up and down the other direction from A. So we'll go up and down 3. 1, 2, 3. And 1, 2, 3. So then what we can do is make a rectangle going through these 4 points, through the vertices and co-vertices. So we go down there and through this co-vertex, through this vertex. So there's that central rectangle of the hyperbola. And then we can go ahead and plot the foci here. So we'll go out left and right, the same direction as A, 5. 1, 2, 3, 4, 5. And same thing over here. Okay, now for the asymptotes, we'd mentioned that they will go through the corners of this central rectangle. So what we need to do here is go through the center and out this other corner. So there's the first asymptote. I kind of missed the middle, but do a better job than me.
Kevin Rogers.
Sorry for the announcement interruption there. Okay, so there's the other asymptote. Okay, and then for drawing the 2 branches of the hyperbola, This is the pretty easy part. You just need to go through the center and then out towards each of the asymptotes, or through the, whoa, let's fix that. Go through the vertex, not the focus, and then out towards the branches. So remember the vertex was sitting right there. I kind of covered it up. The foci will always be inside of the branch here. Okay, and then on the other side, the same thing. Okay. So let's fill in the information below this. So we know it opened left and right, and it was horizontal because the x was first in the equation. The vertices, so those are what the hyperbola is actually touching there. So we've got negative 1, 2, 3, negative 1, 2, 3. So negative 3, negative 3. And 1, 2, 3, 4, 5, 6. No. 1, 2, 3, 4, 5. Negative 1, 2, 3. So 5, negative 3. Vertices right there. Okay, the co-vertices, the top and bottom points here. So we've got 1, 0, and 1, negative 6. The foci are the points on the inside of the branches here, and we've got 6, negative 3, and negative 4, negative 3. Now the length of the transverse axis, remember that's the distance between the vertices. So if a vertex, the measurement of it from the center to a vertex is a, the length of the transverse axis is going to be 2a, like the major axis was. So we have 8, because a was 4, so 2a is 8. And the conjugate axis is going to go between the covertices, and that'll be 2 times b, so that's 6. E is still the same formula we've had before, c divided by a. So c was 5, and a was 4. And that is equal to 1.25. And again, that's just telling us how far apart or how wide the hyperbola is. The greater the eccentricity, the wider the hyperbola. This is still pretty close to 1, so it's not too stretched out. And then we have the equations of the asymptotes. Those are the dashed diagonal lines going through the corners of our central rectangle. So the way we're going to do these is we're going to use that y minus y1 equals m times x minus x1. We can figure out, well, we know where the center is, so we can use that point. So the center was at 1, negative 3. So we have y minus a negative 3 or plus 3. And we can figure out the slope of these asymptotes because we know what corners they go through. It goes through the center, and it goes through these corners here. So we'll have 2 different lines. So going from the center up, we're going to go up 1, 2, 3 over 1, 2, 3, 4. So we'll have a positive 3/4 slope for the asymptotes. We have positive 3/4. But if we go down to the other corner, we go down negative 1, 2, 3 over 4. So we have plus and minus negative 3/4. So our slope, we're going to have to do this twice, but for the slope, for m, we'll have plus and minus 3/4, and then x minus the x value of the center, which was 1. So then, let's do both of these. So if I distribute the positive 3/4, so I have y plus 3 equals 3/4 x, and then positive 3/4 times negative 1 is positive 3/4. And then if I subtract the 3 over, and you'll get a common denominator there of 4, then that one will become y equals 3/4 x minus 15 over 4. And then if we distributed the negative 3/4, we'd have y plus 3 equals negative 3/4 x Negative 3/4 times negative 1 is positive 3/4. And then if we subtract the 3 over, then we'll end up with y equals negative 3/4 x minus 9/4. So that's probably the worst part of a hyperbola, is having to use to find the equation of the asymptotes. But again, it's just using the center for the x1 and the y1, and then finding the slope, which would be from, you could start from the center going out to the corners of the central rectangle. Then you just solve for y. Let's look at one more. So you have y minus 2 squared over 4 minus x plus 1 squared over 25 equals 1. Okay, so this time the y was first, so that tells us that this is vertical. I'll just go ahead and circle a vertical down there on the bottom. And then the a squared and the b squared always stay in the same spot for a hyperbola. So the center, because the y is first, our center is going to be in the backwards order. So the center is at negative 1, positive 2, opposite sign. A squared was 4, so a is 2. B squared was 25, so b is 5. Then we can use c squared is a squared plus b squared. So we have 4 plus 25. So c squared is 29. So then c would be the square root of 29. And I would have a harder time graphing the square root of 29, so then if I figure out the decimal form of that, it's about 5.38. So that'll be a little bit easier to count on my graph. Okay, so the center is at negative 1, 2. It's vertical, so that means the a and the c value will go vertically as well. So we'll go up and down 2. And then the foci will go up and down 5 and a little bit. So 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5 and a little. And then b will go left and right. So we'll go 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. Okay, so we're not going to connect the c values here, only the a and the b. So then we're going to have this little central rectangle. Let's do it in another color so we can see. Whoops, too far. Okay, and then since we're here, we can sketch in the asymptotes. Okay, and then for this hyperbola, it's vertical, so it's opening up and down. So we start at the vertex and swoop out towards the branches on each side. Remember, you'll never connect the foci. Okay, so there are the two branches opening up and down. Now let's fill in the rest of the information. So for the vertices, that's what got us from the center. We counted out to the a values. So we went up and down 2. So then that would be at the values negative 1, 4 and negative 1, 0. The co-vertices are going left and right here. So we have negative 6, 2 and 4, 2. Then the foci are the points that are just hanging out on their own. And it's off the screen, but we'll have the negative 1, and then the distance from the center to the foci was about 5.38. So if this had a y value of 2, and we add the 5.38, we get 7.38. And then the other one will have an x value of negative 1, but then we'll start at that y value of 2 and subtract the c value, so minus 5.38. And that will be the other foci, so negative 3.38. The length of the transverse axis is always 2 times a, so 2 times 2 is 4. And length of the conjugate axis is always 2 times b. So we get 2 times 5, which is 10. And then E, we have c over a. C was the square root of 29 over a, which was 2. So that's about equal to 2.69. So you can see that's bigger than the previous example, and so these are a little bit further out. Okay. And now for the equations of the asymptotes. So again, we're going to use the center, which was at -1, 2. We're going to use that y minus y1 equals m times x minus x1. So we have y minus 2 equals, so let's go back up to the graph to figure out the slope. Remember, we're going to start from the center, and then we're going to count out to the corners of the central rectangle. So if we're going up, we'll go up 1, 2 over 1, 2, 3, 4, 5. So we'll have a positive 2/5 and a negative 2/5. So we'll have plus and minus 2/5, and then x minus the x value of the center. So x minus a -1 is plus 1. So we'll do this twice, once for the positive and once for the negative. So we'll have y minus 2, and we'll have 2/5 x plus 2/5. And then if you get a common denominator, so if we had -10 over 5, and then we add that over to the other side, we'll end up with y equals 2/5 x plus 12/5. And the other one, y minus 2 is -2/5 x minus 2/5, and then take that negative 10/5 and add it over again. So you'll get y is equal to -2/5 x plus 8/5. Okay, that's it. We'll look at a couple more examples in class together, so just jot down any questions you may have, and we'll address them when I see you next. Hope you have a great evening, and I'll see you later. Bye.